Okay, thank you very much, Tobias, and thank you to all of you for having me today. I want to quickly start by acknowledging a few of my essential collaborators, my graduate student Ryan Brennan at Rutgers, Viraj Pandya, who was an undergraduate at Rutgers, is now in the post-bac program at Princeton, and Ina Choi, who was a graduate student at Princeton and is now a postdoc at Rutgers. So we have a good thing going here. I also want to acknowledge my collaborators in the Candles team. So it's been a very good couple of decades for those of us who work on galaxy formation and on understanding galaxies. We have these beautiful large galaxy surveys like the Sloan, 2DF, Gamma, that allow us to study distribution functions of global galaxy properties like luminosity functions, stellar mass functions, colors, etc., demographics of different types of galaxies, internal structure, sizes, and morphologies, at least for nearby galaxies that are well resolved in these ground-based surveys, and also clustering of galaxies in space. What's perhaps even more exciting, at least for me, is that in the last couple of years, we're now able to do fairly large surveys reaching out to very large cosmic distances, probing very distant galaxies. And so these surveys are centered around high-resolution imaging with the Hubble Space Telescope, but also have a large amount of panchromatic observations from many different facilities: Chandra X-ray telescope, the Spitzer infrared telescope, the Herschel infrared telescope, and so forth, really covering all across the electromagnetic spectrum. And so this allows us to get estimates of physical properties of galaxies, again, like stellar masses, star formation rates, to identify accreting black holes in these galaxies, and to measure the structural properties, and this is a theme of this talk, so things like the sizes, morphologies, and internal structures of these galaxies out to very large distances. So in particular, with the most recent set of surveys with the wide field camera on Hubble Space Telescope, which allows us to image in the near infrared, we can now study galaxies out to redshifts of 2 and 3 in the rest frame optical. And so this has been a crucial advance. And this talk will be rather candles-centric. So candles stands for the cosmic something, 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 extra legacy something. I've been very heavily involved with this survey, even though I can never remember what the acronym means, over the past few years. Yeah, if you can read the Cosmic Assembly, here we go. Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey. Of course, all that matters is that it makes a cute acronym, right? So what CANDLES has done is to image 5 patches of the sky with wide field camera, and there's ancillary data, as I mentioned, from many different telescopes at many different wavelengths. So what we had before these relatively wide field surveys were surveys like the old Hubble Deep Field. So this is a single HST pointing. And these fields are overlaid on what we think the large-scale structure in the dark matter looks like at a redshift of 2. And the point of this diagram is that these fields are very tiny compared to the structures. And so field-to-field variance was a huge issue up until this last generation of surveys. The yellow squares here now show the 5 CANDLES fields, and these are widely separated on the sky. They're each about 1/4 of a square degree. So we have tens of thousands of galaxies, hopefully spanning many different cosmic environments. So hopefully now sample variance will become a more minor issue. So from these kinds of surveys now, we can study how galaxies formed their stars and assembled their stars. So this shows the stellar mass function of galaxies from relatively nearby galaxies out to a redshift of 3. And of course, we see this familiar shape, Schechter function shape, for the galaxy mass function repeated all the way out. But we see significant evolution in the galaxy stellar mass function. So already this is telling us that galaxies are building up their stellar mass over time. And if the dashed line is just repeating this low redshift function so that you can sort of see how much things are changing. And I'll show you a more cartoon sort of diagram. So this is the same results. Whoops. Sorry, I'm a bit unfamiliar with this toy. There we go. So this is showing the same results, now color-coded by redshift. So you can see how the shape of this function is changing over time. And what we can see immediately from this is that at the very massive end, the number density of galaxies hasn't changed very much since a redshift of 2. So these massive galaxies formed very early and rapidly, while the low mass galaxies are still building up their mass. So they've formed much more recently. And by asking how we would have to populate dark matter halos with galaxies in order to reproduce these stellar mass functions, we can get constraints on what we call the stellar fraction, or the fraction of baryons in a dark matter halo that have turned into stars as a function of the halo mass. So that's shown here for many different redshift bins. And so this is a very important constraint on how galaxies populate dark matter halos, right? So we see this interesting result that stellar fractions are low and decreasing in low mass halos. They peak at a halo mass similar to the mass that hosts our Milky Way, and then they decline steeply out into halo masses that host galaxy clusters. Yes? In this case, this is just the central. That's right. It does not. So if you included all of those other stars, it would come up by a factor of a few. It would still decline, but it would come up definitely by, yeah, absolutely, no. So there's different ways you can do this analysis. Okay. So now, if we take our stellar mass measurements for galaxies, and we can also measure their star formation rate, maybe from ultraviolet and infrared observations, we get this kind of diagram of specific star formation rate, so star formation rate per unit stellar mass versus stellar mass. And again, we see something very interesting. There are these two distinct populations of galaxies. We see this rather tight sequence, sometimes called the main sequence for galaxies. And then we see a population of dead, or what are sometimes called quiescent galaxies. And they're rather well separated. So if you just plotted a histogram across this diagram, you would see two rather well separated populations. And so this is shown here for results from the Sloan Digital Sky Survey in the nearby universe. But with candles and other surveys, we can now see these two populations out to a redshift of 3 to 4. So there are still quiescent galaxies out at redshifts of 3 to 4. And this star-forming sequence, although the normalization moves up as we look back further into the past, it remains rather tight all the way back to a redshift of 6, where we can now probe this. I'm sorry, I've cut off the units there. So this is actually, yes, reciprocal years, exactly, in log. Yep. Okay, so now we can imagine doing our counting exercise, right? So astronomers love to count things, and we like to count red butterflies and blue butterflies. So we can draw a line between that star-forming population and that quiescent population, and we can count star-forming galaxies and quiescent galaxies now going back in time in our redshift bins. And we see something now very interesting. So the number, or the mass, contained in star-forming galaxies has not increased very much over the past 12 billion years. But this is weird, right? Because these are the galaxies that are forming new stars. So they should be growing in mass. While the mass in quiescent galaxies has increased by more than an order of magnitude over that same period. But these are not forming new stars, right? So the only logical conclusion, of course, is that something is converting these star-forming galaxies into quiescent galaxies. Something is moving galaxies off of that star-forming sequence down into that dead population. So this has come to be called quenching. And then, of course, the next question is, well, what is doing this quenching? So this is one of the big questions in galaxy formation today, is what's causing this quenching? And so one of the most beautiful results from candles and the related surveys, I think, has allowed us to at least try to pinpoint the cause of this quenching. So now what we're seeing is this same kind of diagram, star formation rate versus stellar mass for nearby galaxies and going out to redshift of 2, 1, and 2. So again, we see our star-forming sequence and our quiescent population. And the color code here is, for the aficionados, the Sursich index. So this is measuring how concentrated the light is in the galaxy. And for the non-aficionados, you can think of this as whether the galaxy is more disk-like or more spheroid-like. Is it dominated by a disk, or is it dominated by a spheroid, or what we would call an elliptical galaxy? So the black and blue colors are more disk-like, and the red are more spheroid-like. So we've known for a long time, right, probably since the 20s or 30s, that disk-dominated galaxies are forming stars, and they're blue, and they're young, and ellipticals are red and dead. But it was a bit of a surprise that this remains the case. There's this very strong correlation between the internal structure of galaxies and their star formation properties all the way out to a redshift of 2. This seems to be imprinted on galaxies in some very fundamental way. In that little cell. Exactly. Yes. Absolutely. So there are actually, I could probably give a whole talk just on this. There are many other papers that have come out just from the Candles collaboration studying these correlations in many, many different ways and slicing and dicing them in many different ways. So it's very fascinating. There's a huge amount of information there, and I apologize for sort of going quickly over it. But yes, so that's just showing this star-forming sequence, sort of the median of where the star-forming galaxies are living. And as I mentioned, that does rise up, yes. Very, very similar, yes. So obviously that's also quite interesting. So the color coding is representing the morphological type of the galaxy, from disk-dominated to spheroid-dominated. Okay. So now we can also study how the light or mass is distributed. So the size, which we might measure with a half-light radius or an effective radius. And so again, for nearby galaxies, we've known for a while that if we look at disk-dominated galaxies, they have this rather shallow relationship between size and mass. Bigger things are bigger. That's fine. And for either the whole galaxy of spheroid-dominated galaxies, or if you just measure the spheroid, you see a much steeper relationship between size and mass. So these spheroid-dominated quiescent galaxies are much more compact than disk-dominated galaxies at a given stellar mass. Sorry, so this is the stellar mass, and this is, let's call it an effective radius. So the radius that contains half of the mass, or light. In this case, it's light. Okay? So it's a measure of the radial size of the galaxy. So now with these deep Hubble surveys a few years back, people started discovering these objects that were sometimes called red nuggets. I don't particularly love that term myself. But these were objects. So now we're seeing the effective radius versus stellar mass in different redshift bins going out to redshift 2. People found these objects which were rather massive, up to 10 to the 11 solar masses in stars. Remember, the stellar mass function is really diving down around that mass. But very small sizes, so sizes of less than a kiloparsec, so very, very compact. But these galaxies that are this compact and this massive, essentially don't exist in the local universe. So they have to disappear somehow. So the question that arises here is, how do these things evolve so much in size without evolving much in mass? Because if they evolved a lot in mass, they would just be more massive than any galaxies that we see in the local universe. So there was a very nice study led by Arjen van der Velde with the Candles team and the 3D HST team, studying the size evolution for both quiescent galaxies. And here, remember, since we saw that very strong correlation, we can kind of think of quiescent galaxies and spheroid-dominated galaxies as to first order equivalent, second order not in interesting ways, but let's ignore that for now. So quiescent or spheroid-dominated galaxies, and for star-forming galaxies. So now we're seeing size versus redshift, where each line is for a fixed bin in stellar mass. Okay, so these are galaxies with stellar masses of 10 to the 11, going down in mass down to 10 to the 10 or 10 to the 9 or so. So an interesting thing is that we see that the evolution of the sizes for quiescent galaxies is much more rapid than the evolution of the sizes of star-forming galaxies. And the evolution of star-forming galaxy sizes seems to be more or less self-similar. So it doesn't depend on the mass. This just sort of shifts down. While for the quiescent galaxies, it seems to depend on the mass. So again, these two different kinds of galaxies, in addition to having different kinds of stellar populations, their structure, their sizes are evolving in very different ways. Well, once you get down to these low masses, now, okay, we can talk about what I think is going on here later if you want, but yes. I don't know why there's no, I think this, no? Yeah, these are the top three. I don't know why there's no symbol there because Sloan should go down that far, so I don't know why we don't have a low redshift point there. Yeah, I agree. It's not a strong breaking at the higher masses. Mm. Yes, yes. Of course. So we have done extensive simulations in the Candles team where we put fake galaxies in our images and we try to redetect them, and we think we understand our selection functions. So we don't think that we are missing. Now, of course, if you had very low surface brightness galaxies, then we would miss them. But we see the distribution of galaxies tailing off well before our detection limit. So we don't see a distribution that disappears into where we become incomplete. So you'd have to have a strange sort of disjoint population of fluffy galaxies. If they exist, we won't see them, but. So this is for the light. So you might worry that maybe the light is just fading out. So people have also done stacking exercises where they stack galaxies to try to see whether there's an extended envelope. And for these very compact early type galaxies, we don't see an extended envelope even when we stack and get down to extremely low levels. So it seems like there's just, this is why they were called red nuggets, because it's really like there's just this very compact little structure there. What's happening to them we'll come to. This is meant to be just, here's what we see. Isn't this interesting, right? So believe me, I will come to what I think is happening to them. Okay, so now we can start to put some of these different properties together into a diagram, which is a little bit unfamiliar, so let me sort of walk through it a bit. So we had, go back. We had the star formation rate versus stellar mass diagram, and we said, okay, we can draw a line here to separate our star-forming galaxies from our dead galaxies. Okay, and now we had our size versus mass diagram. So imagine we did the same thing. We draw a line that's parallel to the observed sequence to separate our extended galaxies and our compact galaxies. And if we make this line parallel to the observed sequence, then everything is mass independent, right? So we can shift up and down in mass, and it shouldn't matter. Okay, so we can take a bin in mass or cut in mass, whatever we want. And now we can plot specific star formation rate, so star formation rate divided by mass. And it turns out the slope of this line is about 1.5. So we're going to take the stellar mass and divide it by the effective radius to the 1.5 power. That seems weird, but it's just so that we stay parallel. Okay? And I'm going to call this the compactness. So you'll see this sigma or sigma 1.5. But again, it's just a measure of how extended the light is in the galaxy. So now this shows little postage stamps of galaxies at a redshift between 2 and 3 from Candles. And you can see that these extended star-forming galaxies, so these have low compactness, they're extended, look like disks, sort of. I mean, they're not like grand design spirals, but these are the disks that we see at redshift 2. Well, as I said, they are very different from nearby disks, but if you actually go and take IFU data, they're supported by rotation, okay? And they have exponential light profiles, more or less. So these are as disky as we get. Yes, H-band, observed H-band. Yes, yes. So we've also done shape-based estimates, and these also they have shapes like disks. Is there another question? Okay. All right, so now if we come over to this quadrant, which is star-forming compact galaxies, right? So these have high compactness, they're compact. And they might look red in this picture, in this H-band picture, but these are detected in the infrared. So these are dusty, highly star-forming galaxies that are very compact. And then we see things that also look red, but this time they're red and dead. We don't see any infrared. And again, they're very compact. Notice we don't see anything in here. We don't see any quiescent extended galaxies at a redshift of 2 to 3. All right? Because we see MIPS 24 micron, we see Herschel 100 micron, we see ultraviolet flux. In some cases, yes. Actually, in I think all cases, the UV is at least detected in all of those objects. That's right. That's right. Now, as you can see, they're rather clumpy, so yes. Okay, so now we can look at this diagram in redshift slices, going down from redshift 3 to redshift 0.5. And these lines are just sort of to guide your eye to see these different quadrants of, again, extended star forming, compact star forming, compact quiescent, and extended quiescent. And what you can see is that galaxies seem to be first moving down, becoming quenched, becoming quiescent, and then they start to populate this quadrant. So as we go down in redshift, the galaxies start to populate this extended quiescent quadrant. So here's the cartoon version of this diagram that we published in a paper led by Guillermo Barro with the Candles team, suggesting that galaxies might travel on these two different tracks. So disk-dominated galaxies didn't really do much. They stay fairly blue and star-forming. They maybe get a little bit more extended, while spheroid-dominated galaxies evolve along this, what we call the fast track. So they become quenched, and then they become extended. And again, I'll talk about what I think is going on here a little bit later. Why is there not a track for fading disks? We can't, and in fact, we do see some, but we don't see many. So that would just be a disk that the star formation just shuts down. So that would be something that went straight down, right? That went down here. And yes, some galaxies do, but they S0s, yeah. They do exist, and probably if you go and look in really dense environments, probably more of them exist. We're still not probing very dense environments with candles so much. In the observations, exactly. Yep. Yep. Yeah. Correct. Correct. Yeah. And what we're yes. But this is a fair question, right? We're arguing that it's getting populated like this, right? And Jenny's asking, well, why can't these just go down? And they could. They could. However, if you then go and look at the Sursich indices of these guys, which we've done, they look like ellipticals. Most of them don't look like disks. Morphology, light profile, distribution. All right. Okay, so just to sort of summarize the first part here, what we've been seeing, I think perhaps the main point to take away is that for the first time, we can simultaneously probe the internal structure of galaxies, these sizes, densities, internal densities, morphologies, out to redshifts of 2 to 3, and their stellar population properties. And what we've seen is that the star formation activity and the internal structure and morphology are linked in these interesting ways and are evolving in these interesting ways. All right, so now let me come to trying to interpret these results. So perhaps the most obvious way to do this is within this standard paradigm of the cold-dark matter hierarchical structure formation scenario. So the structure formation of the dark matter, as you all know, is driven by gravitational instability in an expanding universe. And then this is sort of a laundry list of probably a minimal set of physics that we think we need to include in a model of galaxy formation in a cosmological context. Some of these are obvious. You know, you need to understand how gas is shock heating and cooling and accreting onto galaxies. You need to understand how stars are forming, right? Some of these I think are less obvious. So I think almost everyone in the community now thinks that we need to understand how black holes form and grow and evolve and interact with galaxies in order to understand how galaxies form. And this is relatively new, right? So these communities didn't talk to each other very much when I was in graduate school. And over the past 10 years, I think we've all realized that we probably are not going to get galaxies right unless we understand what the black holes are doing. All right, so this is the reason this is a very, very difficult problem, right? If we need to understand what stars, supernovae, and black holes are doing down on scales of parsecs or subparsecs, and how this all interacts with giant molecular clouds and spiral arms and bars and galaxy environments and groups and clusters and the cosmic web, etc., then we really have, depending on exactly how you count it, something like 7 or 8, maybe 9 orders of magnitude of dynamic range. So you can't just put this in your computer and do it, right? And in addition, of course, I argued that this is a minimal list of physical processes, but it's probably not a complete list. I mean, it's certainly not a complete list. So it may well be that, you know, magnetic fields or cosmic rays or turbulence or, you know, something that I've left out here is also critical to understanding galaxies, and we for the most part, don't know how to put that into our cosmological simulations yet. All right, so as a result, the way that the community is approaching this right now is you do a simulation, and on some scale, you say, well, I don't really know what's happening below that scale, and that scale varies depending on, you know, what you're trying to do. So below that scale, I'm going to put in some kind of phenomenological recipe, sometimes called a subgrid recipe. And because I have to parameterize that, I have to set the values of those parameters somehow. And so I'm probably going to do that by trying to match some kind of observation. So I use some observation as a calibration to set the values of these parameters. So you form small galaxies and merge them, but you also accrete a lot of stuff along the way. Okay, so yes, we'll come to that a bit more. So one way to handle this problem is to use a technique called semi-analytic modeling, in which we simulate the growth of structure in the dark matter as cheaply as we can, so using a dissipationless simulation with only dark matter in it. And then we can track how dark matter halos build up over time. This is represented with a merger tree, so the x-axis means nothing here, and the size of the symbol just shows you the mass of different lumps of dark matter that are merging together and building up to form a bigger halo. And then within each of these halos, we have basically simple spherical cow kinds of approximations. They're based on physics. It's, you know, simplified models, but they're based on physical principles that tell us how much gas accretes into the halo and cools, forms stars, produces heavy elements, etc., forms black holes. You know, you can put in whatever you like. And then, as I mentioned, we calibrate these recipes by matching certain observations. And in many cases, we also check that we get the same answer as what you would get with a fully numerical simulation. Yeah. Yes. Yes. Okay, so in detail, in every semi-analytic model, you decide what is the smallest mass halo that I care about, and you might pick that to be, the lowest temperature where atomic radiative processes can cool gas. And then below that, you just call it diffuse matter, and that's tracked. So I haven't shown it here, but there should be another sort of channel of what we call diffuse accretion. And the idea is no galaxies can form, so we're just going to consider that to be diffuse gas accreting onto the halo. Yes. Yes, and that again is still coming from the dark matter only simulation. So that's telling you how much of that diffuse mass is coming in. Absolutely. Mm-hmm. This is one kind of technique. They're all approximations set within the merger trees from the n-body simulations. Okay, so this is one technique. And this, this has a very extensive literature. There are many, many papers. There's a long history to using these kinds of techniques. And of course, the advantage to these techniques is that they're very, very computationally efficient. So, I can run a simulation with 2 million galaxies overnight on my little Mac desktop. And what that means is that if I don't understand the details of all of these physical processes that I've been listing, I can try lots of different things. I can even, do things like a Markov chain Monte Carlo approach to explore my parameter space. So there's a lot of things, there's a lot of exploration that you can do very efficiently with these techniques. And so over the past, going on 25 years now or so, if we look back to that first White and Frank reference, based on these techniques, we've built up a qualitative picture for galaxy formation that does explain many of these correlations that we see. So for example, this gray line here is schematically representing that fraction of stars per halo. So the fraction of baryons that manage to form stars in a halo, which as we saw from the empirical constraints, this has this shape, right? So in the semi-analytic models, we can reproduce this with a model in which feedback from massive stars and supernovae has a larger and larger effect as you go into lower and lower mass halos. Makes sense, right? There's smaller potential wells, so it's just easier to expel the gas from those halos. So that has an increasing effect, causing this fraction of stars to go down, while in massive halos, these halos can more readily form supermassive black holes. And if we account for the energy being emitted in, for example, these giant radio jets, couple that to the gas that's cooling, then most of the gas in these large halos stays hot. Of course, that is consistent with observations of the X-ray gas halos in these objects. So there's very little cold gas in these objects. And that causes this downturn here. So the peak in this picture is coming from the fact that one process is ramping down this way, the other process is ramping down that way, and here's sort of where they cross. But in addition to that, it makes some other interesting predictions. So for example, down here, galaxies acquire most of their stellar mass by accreting diffuse gas and turning it into stars within the stellar body of that galaxy. So what we would call in situ formation. And so they tend to be mostly disk-dominated. Up here, because of the shutoff of the cold gas supply, you have this merging hierarchy that we saw before, but now we're merging dissipationless purely stellar objects. And so that has a very strong effect on the morphology and the structures of those galaxies. So this picture, as I said, can qualitatively account for a lot of these different correlations. Now, again, it's all built on these very simple approximations. So, there are people who have the very reasonable reaction that, well, yes, this is very nice, but, what if your approximations are all wrong? Fair enough. Absolutely fair enough. So, of course, it's useful to do the same kinds of experiments where we try to model the physics in more detail. So here, instead of just sort of tracking these general flows, we're actually solving the equations of gravity, hydrodynamics, thermodynamics, etc., either for particles or for grid cells, and actually tracking how the gas and stars move around, as well as how stars form, etc. Now, once again, we have a resolution. And below that resolution, we put in assumptions. We put in phenomenological recipes. So for example, in most cosmological simulations, the smoothing length, the spatial resolution, is around half a kiloparsec. Maybe a couple hundred parsecs if you're lucky. So on scales less than that, you have a bunch of gas, and you have some recipe for how that turns into stars, and then how the energy momentum coming out from those stars couples with the gas. So just keep in mind that, yes, this is a much more detailed calculation of some of the physics, but a lot of the physics is actually very similar to what's going into these simpler models. And I also feel like people sometimes tend to forget, you see these beautiful pictures and beautiful movies from these simulations, and it's wonderful. But in order to make galaxies work at all, we have to do some dirty tricks in these numerical simulations. For example, I don't want to belabor this, we can't resolve a multi-phase ISM, right? We can't resolve these dense molecular clouds sitting within a much more tenuous and warmer phase of gas. And so well, it's both. It's both, right? So most of these simulations are not trying to track how molecular gas forms out of neutral gas, right? But it's also, why would you try when you can't even resolve, right? So they're coupled problems. Okay, so what's meant by this is that you have a parcel of gas and gravity is trying to make it collapse. You put in an effective equation of state that has an extra pressure, and one imagines that this pressure is coming from feedback, right, from stars, or turbulence, or something else that you're not explicitly putting in, but it prevents that gas from collapsing. So it's yes. Yes. Well, and if you don't, exactly. If you don't do this, what people found in the early aughts was that, when they tried to simulate gas-rich galaxies, they fragmented all over the place. So this was to prevent this fragmentation. Okay, I don't want to belabor this point. Thank you. Okay. So here are some examples from some well-known simulations that some of you may have heard about. So this is showing results from the Illustrious simulation, which was carried out with a code called a repo, which is a moving mesh code. Okay, so it's a grid-based code. It's very, very clever. So the cells move around to track where the matter is. And so what you see here is the dark matter density from redshift 4 to 0, and then the gas density. This is about 100 megaparsecs on a side here, and the slice here is, I think, around 10 megaparsecs, something like that. And then the colors here are showing the temperature of the gas and the metallicity of the gas. And one thing that I think is really interesting, which maybe we sort of forget to notice, is that the gas density does trace the dark matter density really pretty well. So gravity is really, really important at bringing gas into galaxies. It may seem like a trivial point, but you do these fancy simulations, and this is one of the things that comes out. Now, in this simulation, so I was going on about the subgrid recipes that are used here. This does use this stiff equation of state, so this subgrid treatment of the ISM. And in order to model winds from stars and supernovae, they kick particles, so they give a velocity to particles around forming stars in order to match scaling relations for large-scale outflow rates from galaxies. And those scaling relations are essentially identical to what we typically put into semi-analytic models. So this is, I think, a nice example of a lot of the subgrid recipes being very similar, but some of the physics is being simulated in much more detail. Then there's also another recent simulation. This is a similar sized box shown here. I love this representation that they've done here. So here, the color represents the temperature of the gas, and the intensity represents the density of the gas. So this is from the Eagle suite of simulations. And here they still have a certain set of tricks for modeling these small-scale processes of star formation, stellar-driven winds, black hole formation and growth, AGN feedback, etc. But they're all done a little bit differently. So here, instead of kicking particles, they're putting in thermal energy. But as many of you may know, if you just put in the thermal energy from stars, it cools away and doesn't do anything. Right? So this has been a problem for years and years. So their way of getting around this is to say, okay, I'm going to allow each particle to build up thermal energy until I heat to a certain critical temperature, which is pretty hot. So of order 10 to the 7 Kelvin or so. And only then am I going to heat my particle. But then I'm going to heat it up a lot. Right? And that seems to be quite effective at driving a wind that gets gas out of the galaxy, which is what you need to do. All right. And for so these simulations have a uniform metagalactic photoionizing background, which is included. But yes, that's actually a great point. None of these simulations are doing self-consistent radiative transfer. They are not including the radiation fields self-consistently. Yeah, there's shock heating to the extent that these techniques can capture it. And actually, they're pretty good now. So this is a smooth particle hydrodynamics simulation. Yeah, so a lot of this red stuff here is heated due to shocks as the gas collapses into those halos. Some of it is also heated by the AGN feedback and the stellar feedback. But even if you switched all of that off, you would see this shock-heated gas in these dense regions. Yes. That's exactly right. That's exactly right. So you say, I imagine what's happening down on these scales, and I try to mock that up somehow. And people are doing this in different ways. So I think this is the crucial point. People are doing this in different ways, and so we can see what difference it makes. I think it's worth doing. Okay, so this plot is from a review article that I recently completed with my wonderful collaborator and co-author, Ramil Dave. It will appear in volume 53 of Annual Reviews of Astronomy and Astrophysics, and I'd be happy to share it with anyone who's interested. So what we did was to gather predictions from several different sets of these numerical hydrodynamic simulations, including Eagle, Illustris, and also the Dave and Oppenheimer simulations, and 5 different semi-analytic models. So, many different groups. Everyone's done their own thing. We didn't try to get people to do the same thing at all. We just said, send us your models. And so what you see here is the stellar mass function that we saw before in some different redshift bins. The black points are a compilation of observations. We took a lot of care to try to do the best observational compilation. And then, so the different lines are these different models. The dashed lines are the 3 numerical hydro simulations, and the solid lines are various different semi-analytic models. And the shocking thing to me, okay, so first of all, these simulations took millions of CPU hours on the world's biggest computers. The semi-analytic models, as I mentioned, you can run on your laptop. I don't look at this and say, wow, those semi-analytic models are just terrible, right? Or, oh, the Eagle simulation, just, they're very similar. Now, all of these simulations and models, yes, you're absolutely right. You're absolutely right. So this stellar mass function was directly used to tune these recipes. So no surprise at all that these agree. But these observations were not used to tune. And in fact, you can see that the simulations do not match the observations, and they don't match the observations in the same way, in the same sense. They're wrong in the same way. And that makes us think maybe, maybe this actually means something. Over here? These gray ones? They're all the symbols are observations, and they're just different symbol types in case you wanted to figure out exactly which observations they were. I don't think it's too important because I think the observations are mostly consistent. Up here? Yeah, look how big the error bars are here. I mean, I wouldn't, the things get dicey when you try to measure stellar masses at redshift 4. So I wouldn't put much stock in those. Yeah. Okay. So there's a whole bunch of these comparisons of different things in the review article. Here's just one more example of this. So this is the star-forming main sequence, star formation rate versus stellar mass. Again, the symbols show observations. And once again, the model predictions are very convergent, although they are starting to diverge a bit as we get up to redshift 4. And very interestingly, one can actually describe the behavior of these very complex, very expensive simulations by an even simpler model than a semi-analytic model. And this is sometimes called the equilibrium model, or sometimes called the bathtub model. Some of you may have heard these names bandied around. And this is basically the assumption that the rate of accretion, so the rate that gas comes into galaxies, is exactly balanced by the rate that gas is turned into stars and the rate that gas is ejected from galaxies, right? So you have an inflow term, you have a consumption term, and you have an outflow term. And basically you set those equal and you get this evolution. The evolution of the models. The universe doesn't seem to work quite that way. It almost works that way, but there's this interesting deviation. And again, the models all deviate from the observations. But there's nothing to say that that outflow rate has to balance the inflow, right? You could build up gas inside the galaxy, right? Yes, absolutely. In detail, right? So in detail, if you're doing a simulation where you're actually kicking particles or heating particles, then sure, it's much harder to get out if you're down in a deep potential well. But what this is saying something much more general, right? Which is that there seems to be this cosmic equilibrium in galaxies, which is not, it's not obvious, I think, that this should be the case. And in fact, as I mentioned, the universe doesn't exactly behave that way, but it almost behaves that way, which is, interesting. Absolutely. So the observations may be wrong, right? I forget who the quote is, right? That if your model matches all of the observations, the model's wrong because some of the observations are wrong. Yeah. So, absolutely. Yep. Yes. 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 Well, so remember that everyone is tuning their models at redshift 0. So again, that's a selection effect that we all try to match local observations. That's just a sociological phenomenon. you could, if you wanted to, you could try to match redshift 4, and maybe that would be a good thing to do. Right, right. The point is that the evolution is different. That's the, yeah. Well, so actually, yes, so it's actually slightly more interesting. We can make this diagram out to redshift 8 now, and of course you can stop believing it wherever you like. The models match the observations really well from redshift 8 to roughly 4. Then they don't match between redshift 4 and roughly 1-ish, 0.5-ish, and then of course, we've pinned them here. So they match really well at very high redshift, but somehow in the intermediate regime, things are something different is happening. There's something we don't understand there. Yes, so that was the very first plot that I showed you. Galaxies are building up their mass. We see more and more galaxies over time. We see more massive galaxies over time. So yes, they're building up their mass. Okay. Peaks and the black hole accretion rate. Yes, yes. Lots of stuff is happening. Yeah. All right. So some people, including our group, have also checked whether these models, which remember are invoking black holes and black hole feedback to match our galaxy properties, we thought, well, we'd better check whether we see the right number of bright AGN or quasars in AGN. So this shows the luminosity function of quasars and AGN. The black points are the observations, and the colored points are our models. And we can play with these subgrade recipes for how black holes grow and accrete gas, etc. But we do pretty well. So these models do pretty well at matching the evolution of the number of accreting black holes over time. And an ongoing question that we're interested in is to then say, okay, well, what do the galaxies that host these accreting black holes look like? What are their properties? And to see whether the predictions of our models agree with observations, because of course we do have a lot of information on that, though it's tricky to even ask that question. Okay, so the takeaway point, part 2, is that for years and years, we've struggled to reproduce even basic observations of galaxies, things like the stellar mass function or luminosity function, in this paradigm of hierarchical structure formation. And now we can do a pretty good job. So this is quite exciting, I think. And in addition, different groups using different techniques and different methods, different kinds of approximations, are getting pretty similar results, pretty convergent results. So even though we're relying on these somewhat arbitrary subgrid recipes, and we're all doing that a little bit differently, for the global properties of galaxies, that doesn't seem to be a huge effect. It's a small effect. And in fact, that seems to dominate the remaining differences and uncertainties in our models, this treatment of subgrid physics. Is there a question back there? I'm sorry, what applies? Yes. I'm including the data at every redshift where we have data. So I think, broad brush for these global evolution, we're doing, we're agreeing at levels of factors of 2. That's okay. That's pretty good, right? We're not an order of magnitude off anymore, which we used to be. Okay. So now I want to come to the question, which was planted in your minds at the beginning of the talk, of what the internal structure of galaxies tells us about this physics of galaxy formation. So, just not that I need to remind you, but if you look at images of galaxies, we see these very complex structures. We see galaxies of different types, different sizes, etc., as we talked about already. So what do we learn from that? And I already sort of gave a very brief overview of this basic picture for why we see these different types of galaxies. So the cartoon picture is that we have this smooth accretion of gas that forms rotationally supported disks. And this gas has some angular momentum because of tidal torques in the early universe. And so that settles until the angular momentum supports the disks. And then we have this fundamental prediction of the hierarchical picture that galaxies are merging all the time. And mergers can transform galaxy morphology, as I already mentioned. And in this picture, mergers also drive gas into the centers of galaxies and build the supermassive black holes. So mergers, rapid black hole growth, and morphological transformation are all connected in this picture, in this model. Now, of course, that may all be wrong, but this is the picture that we're working with here. Mergers of galaxies. Well, first the halos merge, and then it takes a little bit longer for the galaxies to merge. But eventually, unless the galaxy gets tidally destroyed, they're going to merge. Depends on the halos. Some halos do, some halos don't. They're merging. There's mergers going on throughout cosmic history. And we can track that with the simulations, right? Okay, so let's see how this picture, and now we're back to the semi-analytic modeling picture. We don't yet have predictions for how galaxies of different morphologies evolve from these large cosmological simulations. We will very soon. But for now, we're using a semi-analytic model. And we're using our results from candles. So these are hot off the press observational results to ask what's the fraction of galaxies, what's the fraction of galaxies that are quiescent, so those quenched galaxies, over time, and what's the fraction of galaxies that are spheroid dominated, so that are dominated by their bulbs or their spheroids. So the black line here is the measurement from candles at high redshift, and at low redshift we use the gamma survey, which has a large volume. And then these two lines here are the predictions of our semi-analytic models. And the difference between the two lines is, so one of the nice things about semi-analytic models is that it's very easy to switch things on and off, right? So it's very easy to say, well, I only build spheroids in mergers. Or to say, no, I think that sometimes also the gas doesn't have enough angular momentum to support it, and it's going to have an internal instability and form a spheroid in that way. So that's the difference between these two lines. And it turns out that if we only build spheroids through mergers, we don't get quite enough spheroids to match the observations. So we need to put in this additional way to make spheroids, which is what we call a disk instability. But again, if you sort of squint at this, it looks pretty good. It matches the observations pretty well. And again, these observations are brand new. We didn't tune to these observations. Yes? It's basically, right, so the disk is supposed to be supported by its rotation. But if you don't have enough angular momentum to support the disk, then it's going to keep falling in. So you could imagine you have a disk, and then it accretes some more gas, and it goes over that. It's like a Tumra condition for stability, right? And then the gas is going to lose angular momentum and move in and form a spheroid. That's the idea. In detail, it's a Tumra-like criterion. Okay. So yes, it is formally a big discrepancy. Once again, this relies on measuring star formation rates at redshift 2, which, as you pointed out, is hard. Yeah, we don't have real error bars on the star formation rates. So the error bars here are, as you can see, I keep doing that. The error bars here are actually dominated by the field-to-field variance. But we don't have a really good propagation of our errors on the star formation rates because the observers just sort of go, well, we did our best, Okay. So now we've said, okay, the overall number of quiescent galaxies and star-forming galaxies seems to be reproduced pretty well here. Let's try to estimate the sizes of our galaxies and how they're evolving with time. So the simplest model we can imagine, again, back in spherical cow world, is we have some angular momentum. We know how much that is from the simulation. And again, the gas just collapses until it's supported by its angular momentum. So in that case, the size of the disk is going to be proportional to the amount of angular momentum. This is the dimensionless spin parameter times the initial radius, so something like the virial radius of the halo. And there's some small corrections that you put in here that have to do with the fact that as the baryons fall in, they actually modify the density profile of the halo. Okay, so then recently we decided to develop a new model for estimating the sizes of spheroids that form in these mergers and disk instabilities. And once again, we just sort of use the simplest idea we could think of, which is conservation of energy, right? So you have two progenitors, you combine them. The energy has to be the energy in the progenitors, the energy of the orbit, and you have to subtract any energy that gets dissipated by cooling. Okay, so if you have a gas-rich galaxy, then the remnant is going to be smaller than this, or more compact than the progenitors because of this dissipation. If you have a galaxy with no gas, a gas-poor galaxy, then if you just do this simple calculation, you'll find that it will be less compact than the progenitors. This one? They could, indeed. This is a cartoon. Yeah. You're absolutely right. You're absolutely right. And in the semi-analytic model, we do sort of track things in more detail in that way. But this is a cartoon. Yeah, sorry. Okay. So in the semi-analytic model, we track the mergers. We apply these recipes to compute the sizes of the disks and the spheroids. And remember, disks are being transformed into spheroids, and spheroids are growing new disks all the time. So there's traffic both ways. So what we found is when we compared the predictions of these very simple models with the observations from CANDLE, so these are the same observations I showed you before, shown by the black points, for disk-dominated galaxies from low redshift up to redshift of 2, and for spheroid-dominated galaxies. So the dashed lines here show the composite. This is, again, getting into some details. So we have a disk and a spheroid. We measure the size of the composite, which is what the observers measure. They match the observations very, very well. They match this steeper slope of the size-mass relation for spheroids relative to disks, and they match the more rapid evolution. And all of this is governed by the behavior of gas in these galaxies. So at high redshift, galaxies have a lot of gas, and so when they merge, they dissipate a lot. And that steepens the size-mass relation because those remnants are very compact. But as we go to lower redshift, first of all, we're throwing in bigger galaxies, right? So the disks are a little bit bigger, but also they're more gas-poor, so that term is smaller. We don't get as much steepening. So this explains the difference in evolution and the difference in slopes. So it's all to do with the gas. Okay. And now we can look at things in terms of this Barrow diagram. So think back to the specific star formation rate versus compactness diagram. So these are the same observations I showed you before. And the color code here, again, represents what type of galaxy it is. So Sursich index, or blue is disks going down to red is spheroid-dominated galaxies. And so here are the predictions of the semi-analytic model. And we see the same qualitative trend of galaxies first quenching and moving down and then moving over. And this, again, is because as these galaxies quench, their gas is removed, and so they start having dry mergers, which fluff them up. So now we can put some physical understanding on this picture that we saw before, that the slow track is galaxies that are just quietly sitting around and accreting gas, but sometimes they have a gas-rich merger or a disk instability, which causes them to become very compact. But when they become compact, they feed their black hole, and their black hole starves them of gas, so then they quench, and then the next time they merge, they get fluffy. Okay, so again, this is... Yeah, that's right. Everybody goes through this, yep. Not everybody. So we've looked at this. I didn't put these plots in the talk because I thought I had too much, but I can show you. We've done the analysis to look for that channel. We do see that channel, but it's subdominant. Yeah. Yes, and again, that probably depends on environment. So yes. Okay. I feel like I should probably be wrapping up. Yes, Tobias? Okay. So once again, this is a nice story. I'm going to skip a discussion of stellar feedback in disks. But we'd like to understand the physics of this in more detail. And so this is something I'm working on with Ina Choi and also with Jerry Ostreicher, Torsten Knob, and Ludwig Grosser and Ryan Brennan. So we're using very high resolution zoom-in simulations. So we take a simulation and we re-simulate it at as high resolution as we can. And then we put in every kind of feedback from the black hole that we can think of. So we put in the radiative feedback, we put in the thermal energy, and importantly, unlike all of those other simulations that I showed you, we're also putting in the momentum from the AGN, which we know is very important, right? We see these very fast winds from AGN. And then we can study how that impacts the structure of galaxies. And I hope you can see it on this diagram. So here's a simulation of a galaxy showing the gas with this thermal feedback only, and then with the momentum included. And you can see that the structure, the size, all of these things we've been talking about looks very, very different. So this box is, I'm guessing, but I'm only guessing about 60 kiloparsecs, but I have to, Ina made the plot, sorry. But this is zooming in on an individual halo, right? We have to do this halo by halo. Okay, so let me just show you, in closing, a movie showing the evolution in this compactification space. So this is the same diagram we've seen before, specific star formation rate and compactness for a simulation without AGN feedback and with this momentum and thermal AGN feedback. And then the little images at the bottom show just two simulations, again, with no AGN feedback and with the AGN feedback. So you can see how the galaxies actually look over time. And you can see the little redshift bar at the top. So in the simulation with no AGN feedback, the galaxies quench a little bit, but they don't really quench. And then they keep getting denser and denser. And again, this is because they're still full of gas. So when they merge, they get denser. But in the AGN feedback case, the momentum-driven winds are really removing the gas from the galaxy, and so they quench really hard, again, more like what we see observationally, and they're turning and getting fluffier because of all those dry mergers. And I'll play it one more time, and you can see all the dry mergers. I know, there's too many things going on. I mean, I love this movie, but you need to watch it many, many times. So just watch, you can see the mergers happening, and you can see the the gas being blown out here. So again, each dot is just a particle. It's a very low production value movie, so we're working on doing better movies. Okay, so ongoing work. Again, we can plot where we see the AGN in this diagram and compare that with our simulation predictions. And I'm just going to leave you with my final takeaway messages, and thank you very much. Sorry for going a bit long.